Hey everyone, in today's video, we're going to be solving the problem course schedule on Leetcode. So the question says there are a total of num courses you have to take labeled from 0 to num courses minus 1. You're given an array prerequisites where prerequisites of I is equal to A of I and B of I, which indicates that must take a course BI if you want to take a course AI. For example, the pair 0 1 indicates that you need to take course 0 if you want to take course 1 and return true if you finish all the courses, otherwise returns false. Okay, so this is what the question is, guys. Right now, uh, let's just see what the question is asking us to do. Right, so you're given a prerequisites array, right? A prerequisites requisits prerequisites array, which has AI and BI, and this states that, let's say this is a course one and this is course two, right? So it says that you need to, if you want to take course one, which is A of I, you need to first take course B of I, right? It, for example, over here in 0 1 indicates that to take course 0, you have to first take course 1, right? So over here, in our case, for to take course AI, you have to take course BI, right? So if you have 0 1, so take course 1, you have to take course 0. Sorry, to take course 0, you have to take course 1, right? So this is what it's saying, right? Now, let's imagine this over here, what the scenario is, right? So in our case of 1 and 0, right? In 1 and 0, you need to take course 0 if you want to take course 1, right? So you have to take course 0 first, then you have to take course 1, right? Now, in case of 1 and 2, you have to first take course 1, then only can you take course 2, right? And in case of course 2 and 3, you have to first take course 2, then only can you take course 3. So, can we say that if we order our courses in this sequence 0 1 2 3, right? If we order our courses in this sequence, right, we can take all the courses, right? Because if we take course 1 first, then course second, then course third, course second, course two, then course three as fourth. Then can't we get? Then doesn't the sequence satisfy our condition? Right. What does the question ask? It asks the return true if you can finish all the courses. Right. In this case, we can finish all the courses. If we take course 0 first, then course 1, then course 2, then course 3, we finish all the courses and we can return it true in our case. Right. In this case, right, what are we doing in this case? Right, to take course 1, you have to take course 2 first, right? So course 2 should be before course 1, right? In case of 3 and 4, right, course 3 should be taken before course 4, right? So course 3, then course 4. In this case, when you have course 2 and 4, you have to take course 4 before you can take course 2, which means that course 4 should be taken before 2 and 3 should be before 4. So you can write it like this, right? Can't you? So let me just write it properly. 3 4 2 1. So 3 4 2 1. Right. And in this case, in the last case, when you have course 4 and you have course 1, right, which means that you have to take course 1 before course 4, right? But you have to look at something over here. In this case, when you have to take course 1 before course 4, you have to observe something, that in this case, in the first case, you took course 1 before 2, you had to course 2 before 1, right? This is satisfied, this condition is satisfied. In this case, you took course 3 before course 4, again 3 is before 4, it is satisfied, this is satisfied, right? This is also satisfied. In this case, you have to take course 4 before course 2, this case is also satisfied. But now when you have to take course 1 before course 4, right, if you take course 1 before course 4, you have to write 1 over here, right? And you also have to write 2 over here because 1 is dependent on 2, right? Basically, your course 1 is dependent on 2 because you need to take course 2 before you take course 1, right? But in this case over here, course 4 is dependent on course 2, which means that course 2 is dependent on course 4, which means that you need to take course 4 before you take course 2, right? So you have to again write 4 over here, but you can't do that because in the last case, you want course 4 to be dependent on course 1. You have to take course 1 before course 2, which cannot happen. So you're seeing a pattern over here, right? You can't perform this whole uh, you know this course list because there's a cyclic dependency in our case, right? because we have a cyclic dependency. That's why we cannot perform this. Right. Now, what do we observe over here? Okay, we observe that in our case, this question. So, what do you observe over here, guys? Don't you observe that this question is pretty much similar to the topological sort algorithm, right? So, what does the topological sorting algorithm say? That in a linear ordering of vertices, where you have a edge u, where you have a vertex u and a vertex v and an edge between them, right? Like this. Every time, course u should be edge u should be before v in in a linear order sequencing, right? That is what basically topological sorting is. Right. In this case, it doesn't say the same thing. In case of U and V, they're just giving you the course numbers that course zero should be done before course one. Right. Doesn't this just make this an edge like this, give you the vertex V as one and vertex U as zero? In this case, vertex one is your two U, sorry. In this case, your vertex V is your two. Right. Doesn't it just make like a directed graph for you? Right. And also, you should also understand that topological sorting is based on DAGs, right? It's based on directed acyclic graphs. It doesn't work on cyclic graphs because there is a cycle present in them. All right. And if you want to get a deeper understanding of what topological sorting is, because I'm not going to delve deep into that, right? You need to just check out my previous video, which I put on topological sorting. It'll be linked in the suggestions over here. So do check it out. You'll get an understanding of what topological sorting is before you move on to understand this question. All right. So yeah, in this case, we understood we need to do a topological sorting to get the output. Right. Now, how would we do a topological sorting? Let me just rub all of this. Okay. So don't you think if we create a directed graph for all the nodes over here, right? And so it'll be easier for us to perform, topological sorting on it. I guess that would be the best case scenario. So let's just create like a directed acyclic graph for us. So let me just rub all of this. Okay, right. So let's just create a directed acyclic graph. So in our first case over here, your course one is dependent on course zero, which means that your course zero is dependent on your course one, because your course zero needs to be completed so that you can perform your course one, right? Your edge is going to be from course zero to one because you need to finish course zero so that you can go to course one, right? In your next case, you have to do a course one so that you can go to course two, right? And in your third case, you need to do your course two before you can go to your course three. Right. So don't you get a graph like this, or in even simpler terms, you just get a straight line. If you want to just imagine it, and just in case of simplicity and space over here, we just draw it like this. Right. Isn't the graph basically just this? Right. There are no cycles present in the graph. Now, for the second case, right, let's just draw it again. Your course two, one should be dependent. Your course two is dependent on your course one. Your course one is dependent on your course two. Sorry. That means your course 2 needs to be complete so you can move to your course 1. Your course 3 is dependent on your course 4. Your course 4 is dependent on your course 3, because if your course 3 is completed, then can only you move to course 4. Your course 2 is dependent on your course 4. So if you finish your course 4, then can you only move to course 2. And in your case of 1 and 4, your course 1 needs to be completed so you can move to course 4, like this. Right. Now you observe something over here, don't you? You see that there is a cycle present like this. There is a cycle present in this graph. And topological sorting doesn't work in cyclic graphs. That's why, we couldn't get, that's why we couldn't justify taking all the courses in this question. Right. So doesn't the question just boil down to one small thing? Just find a cycle in a graph, right? That's exactly the whole question over here. If we draw all our courses over here in the form of a DAG, which is a directed, let me just write it over here, which is basically just a directed acyclic graph, right? If we draw our graph in terms of a directed acyclic graph, which is a DAG, we can just identify whether the graph, and later on, and we identify whether the graph has a cycle or not, we can easily just tell whether all these courses are going to be performed or not. Right. So that is what the question is, guys, and this is what you're going to need to do in the question. Right. So let me just rub this and write it down in a stepwise manner. So let me just okay. Let's just rub this out. I hope you understand what we're going to do in the question, guys. This is basically what the whole question is and how it's going to boil down, what it's boiling down to. The very first step that we need to do, we need to convert our prerequisites array in the form of a DAG, and you can do that using creating just creating an adjacency list. Create an adjacency list. That's it. You can just create an adjacency list to portray it as a DAG. Okay. Yeah. Adjacency list. ADJACNCY. Yeah. Create an adjacency list. Right. And step number 2 is just check whether there is a cycle present in the graph. Right. And it's just basically that much. Right. The third step is basically just going to be if there is a cycle present, return false, else return true. So this is what the whole question solution of the question boils down to. The very first step is we need to just convert our question or prerequisites array in the form of a DAG. Right? And we can do that by just creating an adjacency list. Second step is we need to check whether there is a cycle present in the graph. Right? And the third and very last step is you need to check whether cycle present in the graph is the second step, and the third step is that if there is a cycle present, you just need to return a false, which means that you can't take all the courses, right? You can't take all the courses in a justified manner, and if there is no cycle present, which means that you can take all the courses, right? So that is what basically the whole question boils down to, guys. Okay, so now let's see how you're going to solve the problem. So right, let's assume this is our graph given to us: 1, 2, 3. Let's assume this is the graph given to us. What was the very first step? We need to basically, okay, wait, let me just show you what the question would look like. So let's assume that this is our prerequisites array. Let me just write it over here let's say, right in the blue pen. Okay, so let's say prerequisites. Okay, so this is what the question is going to be given to us, right? So the question is going to be given in a manner like this. So 1, 0, 2, 0, 3, 1, and 3, 2. Right. So this is what the question is. Right. Now, since this is our question, let's draw the very first step is to draw a DAG of it. Right. Let's draw a directed acyclic graph. See, firstly, we need to see what is going to be dependent on what. So your I let's assume this is the very first element. Okay, let's not assume anything. Let's just draw it now in a normal fashion. You just see over here that to take course 1, you need to take course 0, right? Which basically means that your course 1 is dependent on your course 0. Basically means that you need to finish course 1 so that you can go take course. You need to take course 0 so that you can take course 1. Similarly, to take course 2, you need to take course 1, right? Again, the next step to take course 1, you need to to take course 3, you need to take course 1, right? So you can draw something like this. And to take course 3, you need to take course 2. So you can draw something like this, right? So this is the very first step for us. Step 1. Okay, we created a DAG, right? We created a DAG. Now we go move on to the second step. The second step Actually, this is again still going to be the first step. Now, the very second step of a first step, the second part of a first step is to create the adjacency list, right? So let's just create an adjacency list over here, right? So our 0 is going to have 1 and 2 and in its list. Our 1 is going to have 3, 2 is going to have 3, and 3 is going to have nothing, right? So this is, now we represented it in a manner of an adjacency list. Now, since we represented in this manner, we basically, in terms of code, we're going to get, just structure. We're just going to get the structure if we represent it in the manner of an adjacency list. So this is a step one done, right? Now, since step one is done, now let's move on to the next step. Okay, let me change the color. Okay, now let's move on to the second step. The second step, right? What was the second step? The second step said, just check whether there is a cycle present in the graph. Right. Now, how can you check whether there's a cycle present in the graph? Right. We already discussed that we can use topological sorting to figure out whether there's a cycle present in the graph. We can use the DFS algorithm to do that. Right. So let's just perform a topological sort over here and see what happens. Okay. So what we're going to do is we're going to maintain a visited array. Okay. The very first step is we're going to maintain a visited array for our nodes. Right. So this is going to be a 0, 0, 0, and 0 for 0, 1, 2, 3. Right. Let me just write in a different color over here. This is for 0, this is for 1, this is for 2, and this is for 3. Okay. We'll maintain a visited array. Right. Now what we're going to do is we're going to loop through all the nodes of the list. Right. We're going to go from node 0 to node 1 to node 2 to node 3. Right. What we're going to do is we're going to maintain a visited array, and then we're going to perform a DFS on our node 0 over here. Right. Now, since we're performing a DFS on our node 0, right, what we'll do is we'll check, can we go inside, as you know what happens in DFS, right? We'll check whether we can go inside these two nodes or not. Yes, we can, because none of them are visited, right? And since DFS of 0 is getting visited, we'll change this to -1, right? Okay. Now, since this is getting changed to -1, right, we'll go to the very first node in a DFS call, which will be DFS of 1, right? We'll perform a DFS call on our node 1 now, right? Our node 1 is getting visited, so let me also cut these values out. So this is getting visited, right? Now we go to node 1 and we visit 3 over here, and we change the visited to -1. Since we change -1, and now we go inside once adjacency once nodes, basically once list over here. Now since we go inside once list, we see that we have 3. We perform a DFS call on 3 now. Right. Now we perform a DFS call in 3. On performing a DFS call in 3, we change this to -1 because 3 is getting visited now. Now we check, we go inside 3's list over here, but there is nothing present inside 3's list. So what we do is we finish up the call, right? So 3's DFS call is getting completed now. It's getting completed, and we go back. But before we go back, what we do is we'll change the value of the visited of -1 over here, the visited value of 3, which is -1, to +1, right? Because the DFS call is getting completed, right? Now, why are we changing this value to +1? What's happening over here, right? Why are we changing this to +1? Is because, as I explained in our previous video on topological sorting, so if we have a graph something like this, right? 0, 1, 2, 3, 4, 5, right? And I create the adjacency list. Let's create the adjacency list of it as well. So 1 has 2, 2 has 3, 3 has 4 and 5, 3 has 4 and 5, 4 has nothing, and 5 has nothing. Right. So what do you observe over here? You observe that to take course 1, you have to finish course 0. To take course 2, you have to finish course 1. To take course 3, you have to finish course 2. To take course 4, you have to finish course 3. Course 5, you need to finish course 3. Right. So what we did was, as in when we performed the DFS calls, right, we were adding them to the stack as well. So when we performed a DFS call on 0, we were adding 0 to the stack, right? Then we moved on to DFS call of 1, right? We went to 1. We performed a DFS call on 1. and we add it to the stack. Then we performed a DFS call on 2. We add it to the stack. Then we performed a DFS call on 3. Right. And then we add it to the stack. And then we performed a DFS call on 4. Right. Now, when we perform a DFS call on 4, we see that 4 has nothing in its list. Right. We just add it over here, but it has nothing in this list. So we can't move forward from 4. Right. So what we did was we popped it out. So we popped 4 out from the stack like this. Right. And the DFS call of 4 was finished. Then we moved back to 3. When we moved back to 3, we saw that 3 had one more element in its list. So this was done. This is done. Yeah, 4 is completed. So now 3 has one more element in its list, which is 5. So we performed a DFS call on 5. And after doing a DFS call on 5, we appended 5 to the stack, right? When we moved to 5, we saw that 5 had nothing in its list. So we popped 5 and we printed it out like this, right? So DFS call of 5 is completed as well. Now we move back to 3. We see that on moving back to 3, the DFS call of 3 is getting complete as well. So we pop it out. Now we move back to 2. DFS call of 2 gets completed. We move back to 1. DFS call of 1 gets completed. Move back to 0. We see that DFS call of 0 is also completed, and we finish it off. So you get something like this. Now, what was the output of this question, right? So to get the sequence, what you had to know that you need to do course 0 to do course 1, to do course, you had to do course 1 to do course 2, you had to do course 2 to do course 3, you had to do course 3 to do course 4 and 5, right? So the output was the reverse of this list, reverse of these popped elements, right? So 0, 1, 2, 3, 5 and 4 was the output. This sequence, if you take the courses in these sequence, then you would have gotten the output. Then you would have done all the courses, right? But one thing to observe over here was that as and when you finished your DFS calls, right? As and when you finished your DFS calls. So when you finish your DFS, let's just jump to 3 in this case, right? When 3's DFS call was completed, right? You saw that the elements that were popped out, right? Those elements were the ones that were dependent on 3, right? Which means that to take course 4 and 5, you needed to take course 3. Right. But over here, when we finished three's DFS call, we popped 3 out of as well, and these 3 elements were there. All right, these 3 elements were there. Let's do it in a red pen. These 3 elements were there. Right. And what you can observe, right? All the elements, including 3, over here inside the list when three's DFS call was completed, all of them were popped out in a topologically sorted manner, which means that the nodes that were dependent on 3, which means that the nodes that needed so the 3 nodes which needed 3 course 3 to be done to be so like 4 course 4 and 5 needed course 3 to be done before it, right? So that they can course 4 and 5 can be done. Those were appended initially. Right. Since course 4 and 5 had nothing in the list, they were added in a single sequence like this. Right. They are not dependent on anyone, so they can be written in any order, 4, 5, or 5, 4. Nothing doesn't matter. But when you finish the DFS call of 3, you see that all the nodes that were ahead of 3 in this graph, like this thing, all the nodes that were ahead of 3 and all the nodes, that were dependent on 3 to be finished first so that they can be done, like 4 and 5, were also added in a topologically sorted manner. They were popped out from the stack in a topologically sorted manner, right? Which means that this portion of your stack is topologically sorted. This means that 3 is done before 4 and 5, right? So basically, this is what it just means that all the nodes that are ahead of 3, right? All the nodes that are dependent on 3, because three's DFS call is completed, which means that all the elements inside three's stack over three's list over here are also traversed, right? So all the nodes that were dependent on 3 to be finished before have also been traversed completely and have been popped from the stack and have been added to the sequence over here, right? This is basically what it just means. Right. So when we move on to 2 now, when we finish two's DFS call, we see that all the elements that are ahead of 2, like these all nodes, including 2 that were ahead of 2, are now added in a list in a topologically sorted manner. These nodes are all added in a topologically sorted manner. Now node 3, which needs node 2 be complete, which needs to be done after node 2, right? Basically node 2 needs to be traversed so that node 3 can be traversed, right, has also been added to the list, and all these 3 nodes are added in a topologically sorted manner. And then we just pop out 2 from the stack and add it over here, right? So we can see when we reverse the list, This node is before 2, and all these nodes over here are added in a topologically sorted manner. The same goes for 1, and the same goes for 0. Right? That is what's happening over here. Now, what's happening over here? Right? We changed it to a plus 1 because its DFS cycle was completed. Now, why are we changing this to a plus 1? This is because in the case of, okay, let's just move forward and you'll understand, I guess. So in this case, our 3 was getting completed, right? We finished 0 1, we finished 1's 3, and we finished 3. Now we finish the DFS cycle of 1 and we change this to a plus 1, right? This is getting finished. Now we go to 2, right? We perform a DFS on 2 over here and we change this to a minus 1, and now we go to 3. Now what happens over here when we go to a 3 is that, let's say I have a node 4 and 5 also like this, which are dependent on node 3. Right. So in our node stack, if in sorry, in our adjacency list, if 3 has 4 and 5 in its list, right? This basically means that if a plus 1 is present over here, right? If a plus 1 is present over here, this means that all the nodes inside the list of 3 are already traversed, right? Which means that they both would also have a plus 1 in their would also have a plus 1 in their visited list, right? Which means that all these three nodes, right? All the nodes, right, when we go from 2 to 3, if it has a plus 1, this means that all the nodes that are dependent on 3, right, all of them are already having a plus 1, so we don't need to go over there. If it has a plus 1, it means that it doesn't have a cycle, and all the nodes ahead of it are already traversed, and they also have a plus 1 in the visited list, right? This is basically what it means. Okay. Now when we go from 2 to 3, if we see that there's a plus 1, we'll just return a true and we'll move on. Okay. Now we go from 2 to 3. If it has a true, we'll just if it has a plus 1, we'll just return a true and move on, and we'll finish 2's DFS cycle, and we'll turn 2 with a plus 1, and we'll return 0 with a plus 1. Right. Now this is what the whole question is, guys. This is how we're going to perform the question. The only important thing you need to understand over here is that about the DFS cycle, if the DFS cycle is getting completed, let me just explain you with a different question also. Let's say if you had like this 1 3 2 and 0, right? And our adjacency list would be something like 0 to 1, 1 to 3, 2 to 0, and 3 to 2, right? If you had an adjacency list something like this, okay, let me just rub this, and we maintained a visited array for us, right? What would happen over here is that we would perform a DFS call on 0. We would perform a DFS call on 0, right? We would have gone to 1, right? We would have performed a DFS call on 1. On performing DFS call on 1, we would have gone to 3. On going to 3, all of them would have become minus 1, minus 1, minus 1. On going to 3, we'd have performed a DFS call on 2, right? And 2 would have also been visited. Now, when we go to 2, we'll see that we would have performed a DFS call on 0 again, right? Now, you would need to understand that the DFS call of 0 was never completed, right? We were still in the same DFS call of 0, where we move on to 1, 3, and 2. But since the DFS call is not completed, we're reaching this point again. We can, we can, manage that state basically of that, the same cycle with keeping a minus 1 over here. Right. Since the DFS call was never completed, this minus 1 will never change. In this case, we were only changing a minus 1 to plus 1 when the DFS call was completed. So we reached from 0 to 1 and 1 to 3. We see that 3 had nothing, and the DFS call of 3 was getting completed. Then only we were changing this to a plus 1. Right. But in this case, since it doesn't, the DFS call is never getting completed and it's reaching to a point where it has again a minus present, right? This means that there is a cycle present, right? You can also see it visually that there is a cycle present in the graph, and we just return a false in this case because we found a cycle, right? This is basically what the question is, guys. Okay, so let's let me just explain you how we're going to solve this through code. So what we do is, if we have a graph like this, Right. Firstly, the very first step is to create the adjacency list. Adjacency, I think it's a pretty obvious way to do it. What you'll do is basically uh, take the adjacency list equal to hash map and equal to dictionary. And what you'll do in the dictionary is you'll do for I in range length of ADJ, AD, ADJ of I of 1 is equal to basically we no, not ADJ of I of 1. So ADJ of prerequisites of I of 1, prerequisites of I of 1 is equal to prerequisites of I of 0. Right. So this is basically just the line of code that you need to use to create the adjacency list. Right. Now, I'm just going to rub this line of code because it's not really that important. I'll just show you in the Leetcode what how this code looks like. It's not that hard also. Okay. So let me just rub this and let's move on to the main important part. So what we'll do is we're going to loop through all the nodes, right? So for I, and before that we're going to create a visited array is equal to 0. Let's just say we're creating something like this 0 0 0 0. Okay. For I in range length of ADJ, will do is if DFS of I visited and ADJ, the adjacency list, we're also passing that, right? If not, okay, so if not, we return a false, and you'll see what we're doing if not and all those things. If not, we return false, else we return a true, right? So this is the main code, and let's write the DFS code again over here. So def DFS I visited and ADJ. Right. Now, what we'll do over here is firstly, we'll check if visited of I is equal to -1. If it is, this means that there is a cycle present, will return false. If visited of I is equal to 1, will return a true, right? Will return a true because as I said, that this node is already visited. This node will get visited, and all the nodes ahead of it are also going to get visited, right? And when we visit all the nodes, all of them get visited in a topologically sorted manner, right? In the example I showed you before, uh, all the nodes are going to get visited in a topologically sorted manner when we pop them out, right? And if we point a one over here, right? So when we go from 0 to 1, right? To 3, and when the DFS call of 3 gets completed, we'll make it a +1. So when we go from 0 to 2 to 3, we see that if it has a +1, it means that the DFS call of 3 was completed, and all the nodes ahead of it would also have completed its DFS cycles, right? Which means that we don't need to go forward, right? Which basically means that there is no cycle present over here. And if you go from 2 to 3 and it has a +1, it means that over this portion would also not have a cycle, right? This portion would also not have a cycle, so we don't need to go with it. We can just return a true in this case. Okay, so this is basically what it is. Okay. Now, now what we'll do is if you're visiting it for the very first time, we'll change it to equal visit of I equal to -1. Okay, simple. Now what we're going to do is we're going to perform a DFS on all the nodes, right? We're going to perform the DFS on all in the adjacency list of our current node, on all the nodes of our current node, right? For j in ADJ of I, right, will do is if not DFS, then we'll just pass j visited and ADJ, right? And lastly, we'll just change our visit when the DFS call is completed. We'll just change this to equal to 1 and we'll return a true. Okay, so this is basically what it is. This is basically what the whole code is, guys. Now let's just understand what's happening over here through the code, right? In the very first step, let's just do a try run to understand what's happening. So in the very first step, right, we go to 0. right? For I in range length of adjacency list, we'll go to a 0, right? We'll go perform it on 0, right? If not, DFS, right? Let's see what not is going to do later. Let's go inside the DFS call over here, right? We'll do a DFS call on 0, right? We're going to do the DFS call on 0 and move on. We go over here. Performing a DFS call on 0, we check that if visited is equal to -1, no, it's not, it's 0. If it is equal to 1, no, it's not, it's equal to 0. And if it's nothing, neither of this, we'll just change it to a -1 over here, right? If you change it to -1, we go inside the adjacency list of adj of I, basically adj of 0, which is the two nodes 1 and 2. So let's say, let me also just make the adjacency list over here. So 0 has 1 and 2, 1 has 3, 2 has 3, and 3 has nothing. So we go inside 1 now, the very first call, right? We perform a DFS call on 1, right? We check if not DFS of J visited and ADJ, right? There's nothing present, so we just perform a DFS call on 1, right? We change when you perform a DFS call on 1, we go back over here, we check if visited of I is equal to -1, if not equal to -1, not equal to 1, so we change this to a -1 over here, right? And then we perform a DFS on 3, right? We perform a DFS on 3 over here like this. After performing a DFS on 3, we again change this to a -1 because these two conditions are not true. We change this to a -1. We go inside the adjacency list. We do a for loop on the list of 3, but there's no nodes present inside it. So basically, three's DFS call is completed, and we change this to equal to +1. Right? This is getting equal to +1, and the DFS call is completed now. Now, and also we return true. Now, in case of DFS of 1 over here, we get return a true. So in this case over here, we return to true. So if not DFS, if not true, this output is returning us a true right now, right? So if not true, basically if false, we're going to return a false, right? If it is giving us a false, we return a false, but it's not giving us a false, right? It's giving uh if not false, right? So if it false, return false. It's not true, right? For this condition to go forward, it should be equal to true, like, right? But this is not equal to true, it's equal to false because we're doing not true. Right, so it's equal to false. So if it's not false, we don't return a false, and we don't return a false, and we move forward. We change the visited of I for this one equal to +1, right? And we move forward and return true. And this is finished. Now for this case, for this 0, we're again getting a true. We're getting a true. So if not true, so if false, if it this basically means if it is false, but it's not the condition can't go forward if it's false. It should be true. So if it's not, the condition can't go forward because it's false. So it won't return a false. We'll change the visitor phi equal to +1. Oh, I'm sorry. We don't change the in this case we're getting a true, right? We don't return a false and we don't move forward because there's one more node which is 2 present inside it. We move forward inside the for loop. Right, we're going to move forward inside the for loop and we perform a DFS call on 2. When you perform a DFS call on 2, we see that these two conditions are not true and we change this to equal to -1. Now we go inside 2's adjacency list. So we perform a DFS call on 3 now. When we perform a DFS call on 3, we see that it is visited. Now, since it is visited, we don't need to do anything because we know that all the nodes ahead of it are now, basically all sorted and there's no cycle present ahead of them. So we'll just return a true in this case. Right. So we just return a true and the DFS call of 2 is getting completed. Right. We return a true in this case again. So it's not returning us true, right? If not, it's not giving if true, it's giving if not true. If not true is equal to false, so we don't go inside this portion. We go inside the visited portion over here. Visited of 1, we change this +1 equal to +1, and this DFS call of 2, which was DFS call of 2, is now getting completed, right? And we return a true. Now when we return a true, right, again for this is going to be a DFS of 0. We see that it is not true. It is this portion is true and the total is not true, which is equal to false. So we won't go inside this. We'll just finish off this visit of 1 and return a true. Right. In the end, we just return a true and the whole DFS cycle of this is completed and we return a true over here. So over here, we return a true for 0. We return a true for 0 over here. Right. And since it's returned true, we see that if not true. So if it's not true, basically means it's false. So we don't go over here, right? And we just return a true, right? But we don't jump over here. We perform the further cycles over here for 1, 2, and 3, right? And in our case, I'll just do it for 0 because this is basically the whole answer. For 1, 2, and 3, you'll just realize that when you go inside 1, you'll see that the visited of 1 is equal to +1, so we return true. If we'll get a true over here for 2, again, it's going to be a +1. For 3, it's going to be a +1. So in the end, we just return a true for all of them. And in the end, we just return a true as the final output, as all the courses can be performed, right? So this is basically what the code is, guys. Let me just show you how the code looks. So this is how the code looks like, right? This is how we're creating the adjacency list, right? We're looping through the num courses. We're creating a list for all the nodes, right? We're creating a list for all the nodes over here, and we're appending a of I of 1 equal to I of 0. So I of 1, basically 0 will have 1 in its adjacency list. Well, 0 will have 1 in its list, right? So to give you an example, what's happening over here, if you had this node, uh, let's go back actually. uh, okay, so let's see over here. Okay, so let's just go back and let me just rub this and show you what that line is just doing. Okay, so what is just happening over here, we're just creating a list of all the nodes from 0 to num courses. So we're creating an adjacency list for all the nodes. So 0 equal to empty list, 1 equal to empty list, 2 equal to empty list, and 3 equal to empty list in this case. Now what we're doing is we're going to loop through the prerequisites array, and we're going to append I of 1. We're going to append in I of 1's list I of 0. So right, we have I of 1 equal to 0, and in 0's list we're going to append 1. In 1's list we're going to append 2. In 2's list we're going to append 3, and 3 is going to be empty. So this is what that line of code is doing and how we're going to create the adjacency list, right? And later on, this is all the code I just told you. We're creating a visited array, we're performing a loop on them, we're doing a DFS call on all of them, and this is the DFS code which I just explained to you guys. So this is the code, guys. Let me just run the code for you. Yeah, it is running and it's submitted. So yeah, guys, it's submitted. So that's all for today's video, guys. If you like the video, do like, share, and subscribe. Do let me in the comments if you what else I can do to explain the concepts better to you guys. Do check out my podcast as well. And there's like a 10% coupon code down below in the description for Geeks for Geeks course if you guys want to check it out. And until next time, guys, thanks for watching.